Hello everyone.
Today we will be discussing few methods by which we can test multivariate normality. In the univariate setup, you have always seen the goodness of fit test, for example, Kolmogorov-Smirnov test or Shapiro-Wilk test. You have also perhaps drawn QQ plot to check normality or any other distribution. So, can we do something similar for multivariate normality? That we will see today. Obvious first question, why do we need to test? We have seen that in the Hotelling t-square test as well as in multivariate ANOVA, our underlying assumption is that every population has multivariate normal distribution. So if I want to validate that assumption, then I need to check the multivariate normality. So we are going to have two different tests, and one other way is via QQ plot. Okay. So first let me go for the tests and then we will discuss QQ plot. So the tests are actually known as tests based on Mardia's skewness and kurtosis measures. Skewness and kurtosis, skewness is related to, skewness is basically third moment and related to third moment, kurtosis is related to fourth moment. So we will see first what do we mean by skewness here and kurtosis here. So these are the formulae. So first we define a quantity called Gij. So what is Gij? Gij is this: yi minus y bar prime sigma hat inverse yj minus y bar. So in Gij we are basically computing something like a quadratic form, but instead of having same vectors on both the sides, we are having two different vectors. So yi is my ith observation, yj is my jth observation, y bar is the overall sample mean. So we are computing Gij. We can obviously see that this is 1 cross 1, so this is a scalar. Now because I have n observations in any sample, I would have n cross n, that is n square values of Gij, right? And we are taking cube of those Gij's and then averaging over it. So we are dividing by n square, adding and dividing by n square. So beta 1 hat p is actually average of all the Gij cubes. Is it okay? Now why is it called skewness? Because as you can see we are taking cube, so it's something related to skewness. Not exactly skewness, but something related to skewness. Similarly, we are going to define a kurtosis measure. In that we are going to consider GII. Notice we are not considering Gij now, we are focusing only on GII. So it is exactly a quadratic form: yi minus y bar prime sigma hat inverse yi minus y bar. Okay, and then we are taking square of it. So I have yi here, so I already have yi occurring twice, and then we are taking square. So basically I have kind of like yi raised to 4. I cannot call it y raised to 4 because y is a vector, so raised to 4 is meaningless, but I think you get what I am trying to say. Y is occurring kind of like 4 times, hence it becomes something similar to kurtosis, and we are taking again average. Now because I am considering only GIIs, I have only n quantities, not n square, so beta 2 hat is average of this. Once I have beta 1 hat and beta 2 hat, test statistic is just modification of them. So kappa 1 is a test statistic based on skewness, that is test statistic based on beta 1 hat. So the test statistic is n times beta 1 hat upon 6. This p actually is just to indicate that it is based on p variables. Okay, so it's part of notation. So n beta 1 hat upon 6. This follows chi-square with p into p plus 1 into p plus 2 by 6 degrees of freedom. So as I said, we are not going to discuss derivation of this test statistic. Okay, we are just going to use it directly. So this is a test statistic based on skewness. So once I know that it is chi-square, I can compare the value of this obtained from the given data with chi-square cutoff, and then I can conclude whether the test is accepted or rejected. In fact, I can go one step further and compute p-value also on the basis of this chi-square distribution. So this becomes my kappa 1 becomes my test statistic based on skewness. Similarly, kappa 2 is a test statistic based on kurtosis. So there we subtract p into p plus 2, divide by this, which is kind of variance, and this entire quantity has been shown to have normal 0-1 distribution. Again, we are not going to go into the derivation of this. So once I have beta 2, I will compute this test statistic, compare it with normal cutoff points. So for example, if I want 5%, this is two-sided test, so I will compare it with 1.96. If I want 10% type 1, 10% level of significance, I will compare it with 1.645 and so on. And then we will conclude whether the distribution of the given data is normal or not. Okay, so let me now go back to my question. So the question is, consider iris data set. It is assumed that underlying distribution of each species is multivariate normal if I want to test. Then let us validate this assumption using the test based on Mardia's multivariate skewness and kurtosis measures. So we will consider data specific to one species only. Why? Because two species might have two different means, and if I try to fit a common normal distribution, it may not work. I don't know if you are following me, so let me give you an example. If I consider, say, heights of males and females, and if I plot them together, I might end up getting bimodal curve, one where one mode is near the average height of females, one mode is near the average height of males. Okay, so technically the combined sample may not have normal distribution. Similarly here, the combined sample on the basis of 2 or 3 species may not have normal distribution, but each sample may still have. Sample from each species might still have. So let us try to do this in R. So iris data is already there. I want only one subset of it. So iris 1 to 50, and now I don't need the species name, so -5. Okay, let us check the dimension of this data just to ensure that 50 cross 4. Okay, so we are going to test whether this data set has p-variate, in this case 4-variate normal distribution. So my p is n col of d, n is n row of d. Okay, now I have np. I have to compute gij's first. So let us first start by computing gij. So let me define a matrix called, say, gij mat, because we are going to have n square entries. So it's a matrix with n rows and n columns. So my ijth entry of this matrix will actually be gij. Is it okay? So for I in 1 to n and for j in 1 to n, I need to define gij mat ijth entry as ith observation, so ith row, so di minus mean vector. Let me denote it by mu hat. We are not yet computed, so we'll compute it. Di minus mu hat percent star percent. I should take transpose of this, then sigma inverse. So solve of sig hat and percent star percent, I would do dj minus mu hat. Okay, dj minus mu hat. So I need to first compute mu hat and sigma hat. Mu hat is col means of d, sigma hat is cov of d. If you want, we can maybe print them to see the values roughly. Mu hat is this, sigma hat, let me round off and then let us print it. So round sig hat 2. You should notice that I have not rounded off before, here. In the memory, sigma hat is complete. Only while printing, I have rounded it off. Okay. Okay, so di minus transpose of di minus mu hat, sigma hat inverse dj minus mu hat. So let me try to run this and see if there is any issue. Okay, yeah. So as expected, there is some problem. Sometimes R doesn't understand the vector dimensions. So these sorts of things happen. So let me check. What is dimension of di minus mu hat? Okay. See, this has become 1 cross 4 instead of 4 cross 1. Therefore, this issue. So I'll have to remove transpose from here and put a transpose here. I know this is exactly opposite of what we have learned, but the reason for this is because we are picking ith row, its dimension is 1 cross 4. Okay, so we have to change it accordingly, but otherwise the answer is going to be correct. In fact, I would suggest try computing for 1 or 2 entries and then it would be verified. Okay, we still have an issue. My class of D is data frame, that is the issue. So let us make that as a matrix. So D is as dot matrix D. Now hopefully it will run without errors. Wow. Now, okay. Dimension of this is null because now it has become a vector. So if I see this, what happens? See, this is 1 cross 4. So transpose is now 1 cross 4, which is okay. I think the original one is 4 cross 1. So now I have to put transpose here. I have to remove this. And now let us see again. Okay. Okay, so the reason for doing all these exercises, I know many of you don't have access to laptops, so I am just showing you that even in such a simple command, so many errors can happen. What we should do is, if you first convert it to matrix, then the original formula is going to work. Di minus mu hat prime sigma inverse dj minus mu hat. Okay, so in that case, you don't need to worry much. Okay, so I have my J mat. Let us try to view it. View gij mat. Okay, this is how it is looking. Now from these GIJs I need to compute beta 1 beta 2, and then from beta 1 beta 2 I need to compute kappa 1 kappa 2. So beta 1 by our formula is mean of GIJ cubes. Okay, so I have to do mean gij mat cube. Anyway, I want component wise cube, so I don't need to worry about the fact that this is a matrix. Okay, so I'll get some value of beta 1. Okay, let it be. Then kappa 1 is n beta 1 by 6. Okay, so kappa 1 is n into beta 1 divided by 6. And let us print kappa 1. So 24.15, we have to compare it with chi-square p into p plus 1 into p plus 2 by 6. So degrees of freedom for the first test are p into p plus 1 into p plus 2 by 6, that is 20. So let us check the chi-square cutoff for 0.95. So 0.95 and df equal to df1. Oh, sorry. I want chi-square, not f. It is 31. So actually my calculated value of the test statistic is 24. Calculated value of the test statistic is 24.15. Tabulated value is 31.41. So we are going to accept our H0, and our H0 is the distribution is multivariate normal. So we are going to conclude, at least on the basis of this test, that the first, that is Setosa species, has 4-variate normal distribution. Okay. So this is fine. If I want to compute p-value, I have to see what is p-value. P-value is probability of getting a test statistic value as or more extreme than the current value. So we want 1 minus p chi sq of my current value, that is kappa 1 with the given degrees of freedom. Okay. P chi sq. Okay, so p value is 0.2356, which also, which is expected because we are accepting H0. P value should be larger than 0.05. Okay. Similarly, we have to do for kappa 2. So my beta 2 is actually mean of only the diagonal entries and their squares. So mean of diagonal dij mat and then square of that. Okay, so we first extract the diagonal, take its square and then compute mean. The value is this, and now kappa 2 is, you need numerator as well as denominator because there is some divisor. So it is beta 2 minus something. Let us check the formula. Sorry, beta 2 minus p into p plus 2. Okay, p into p plus 2 and p into p plus 2. Then what is happening? Yeah, I need to go to PDF. Okay, 8p into p plus 2 by n. So square root of 8 into p into p plus 2 by n. Okay, 8p into p plus 2 by n. Let's check the value of kappa 2. Okay, there is some unexpected bracket. Okay, yeah, square root of this bracket is extra. Okay, this value is 0.7587, which is clearly less than 1.96. So we can accept H0 even by this method. If you want p value, I will go for p norm 1 minus p norm at kappa 2. Since it's standard normal, I don't need to give parameters. The p value is 0.2240. Okay, so we are accepting. So in this way, both the test statistic, Mardia's test based on skewness as well as Mardia's test based on kurtosis, both of them are telling me to accept the null hypothesis. Now the next thing is QQ plot. So what is a QQ plot? In QQ plot, of course, as the name is QQ, QQ stands for quantile quantile plot. So on x-axis, I have sample quantiles. On y-axis, I have population quantiles. Actually, it doesn't matter if you change the order. You can have sample quantiles on y-axis and population quantiles on x-axis. That is also perfectly fine. Ideally, if the sample is actually coming from the theoretical population which we are comparing it with, then the sample quantiles and the population quantiles should be more or less same, and hence the graph should be a straight line. Okay, so if x-axis and y-axis are having values which should ideally be same, then the line x equal to y should be a good fit for that scatter plot. So what are sample quantiles? So actually the sample observations themselves we are going to take as quantiles. The only thing is we'll need to order the observations. The lowest observation would be 1 by nth quantile and so on. So let us try to see that in more details. Okay, so in QQ plot we are going to have sample quantiles on say x-axis and population quantiles on y-axis. Okay, sample quantiles on x-axis and population quantiles on y-axis. As I said, if my sample is actually coming from this population, so this is actually the population under consideration. So if I want to test normality, I would have normal quantiles here. If I want to test whether the distribution is say t, I would have quantiles from t over here. So if my sample is actually coming from this population, then sample quantiles should more or less match the population quantiles, and hence the scatter plot should actually be around this straight line of x equal to y. Okay, 45-degree line x equal to y. That's why what we do is we plot these sample quantiles versus population quantiles, then draw the line x equal to y, and if the line is actually matching this scatter, then we say that okay, the QQ plot confirms that this sample is coming from this population. Is it okay? Now what are sample quantiles? So because I have, let us try to understand this in the univariate case. Okay, so I have suppose x1, x2, xn, and I want to check whether they are coming from some particular distribution f. So x1, x2, xn, I have n observations. If I order them, if I consider their ordered statistics, x1, x2, x ordered 1, x ordered 1, x ordered n, then we know from the empirical CDF, I hope everyone remembers empirical CDF that you studied in BSc. At x ordered 1, our empirical CDF is 1 by n. At x ordered 2, it is 2 by n. At x ordered n, it is 1. Of course, I am assuming no ties because we will mostly be dealing with continuous distributions, so no ties. Okay, now, so if this is CDF at this point, this kind of becomes 1 by nth quantile, this becomes 2 by nth quantile, this becomes last quantile, and so on. Okay, so my sample quantiles are going to be nothing but these values. Okay, the ordered statistics from the given data. Now what is population quantile? Now I need corresponding population quantiles. So if I say that CDF at this point is 1 by n, I need to see as per my theoretical CDF which is the point at which CDF becomes 1 by n. Are you getting what I am trying to say? Let me repeat. So what I know is in my sample x ordered 1, whatever is its value, let me say its value is say 2.1. Okay, 2.1 is suppose the smallest observation. What I know is observed CDF or empirical CDF at 2.1 is 1 by n. Then if my theoretical population agrees with this, then the theoretical CDF at some value is going to be 1 by n, and we want that value to be as close to 2.1 as possible. Okay, what was the sign for approximately? It is this. Okay, so we want this value to be approximately close to 2.1. If that happens for each one of these, then I can say that the distribution is good, the fit is good. Then we'll get this type of straight line graph. Getting what I'm trying to say? You may want to go back and rewind this part and listen to it again. So how do I get this point? So I would need to compute inverse CDF of 1 by n.
Okay, then only I get this value. So this value will actually be equal to inverse CDF of 1 by n. Okay, so at what point CDF becomes 1 by n? The theoretical CDF. Everyone is getting what I'm trying to say? Okay, now there is a small catch. If you remember, empirical CDF is always going to be a step function. Even though we know that we are dealing with continuous data, no ties, so ideally my CDF should have been a continuous line or a continuous curve, not necessarily line, a curve, something like this. Whereas empirical CDF is always going to be a step function. It can never be continuous. It's going to be only right continuous. Okay. So to account for this, we need to do what is called as continuity correction. Okay. We need to do something called as continuity correction. Now what is continuity correction? Because we know that before 1 by n I don't want CDF to be 0, and after 1 at the last point I don't want CDF to be 1, and in between points also I need to adjust something. What we'll do is, instead of computing inverse CDF at these points, ideally this is what we are supposed to do, right? We are supposed to compute inverse CDF at 1 by n, 2 by n, n by n, but instead of that we will just subtract 0.5 from each of them. Okay, not here, I'm sorry. We'll just make 1 minus 0.5 by n. This I'll make 2 minus 0.5 by n. So n minus 0.5 by n. Okay. This subtraction of 0.5 is for continuity correction. What happens is, see, suppose my n is 100. Then at the last point CDF was directly becoming 1. Whereas now it would become 99.5 by 100. So it is almost 1, but I'm not jumping to 1. I'm allowing the possibility that, okay, there might be some observations beyond this with very less probability. Okay, so we will compute inverse CDF at these points. So I would compute F inverse at this, F inverse at this, F inverse at this. Let those be called as y1, y2, yn. Okay, and ideally my x ordered one should be similar as y1. X ordered 2 would almost be same as y2. X ordered n should almost be same as yn if the theoretical and sample population match. Okay, so this is what we have to do. So we have to get ordered statistics as sample quantiles, and y1, y2, yn obtained by this method, computing inverse CDF at 1 minus 0.5 by n, 2 minus 0.5 by n minus 0.5 by n. These become my population quantiles, and then we would plot x1, y1, x2, y2, xn, yn. Is it okay? So as I said, this is all okay in univariate setup. Now you must be thinking, how can I order in multivariate setup? Of course, we have discussed that in the multivariate setup, ordering is not possible. So what I'll do is, okay, if I am not comfortable somewhere, let's run away. So let's go to univariate setup. We know that quadratic form of multivariate normal has chi-square distribution. So we would draw QQ plot using chi-square instead of multivariate normal. And that chi-square is actually univariate chi-square. So we can use this theory that we have with us. Okay. So what I'll do is, I'll first compute quadratic form for every observation that I have. So I'll get n values of the quadratic form. Let me call them Q1, Q2, Qn, where Q1 is x1 minus x bar prime sigma hat inverse x1 minus x bar, and so on. Then we will order these. So I will have Q ordered 1, Q ordered 2, Q ordered n. Actually, ideally I should write small q, but it's okay. So these become my sample quantiles, and then theoretical quantiles we would compute by this method, by computing F inverse from chi-square with p degrees of freedom. Okay, so let us now do all these things in R.
Okay, so first I need to compute sample quantiles. So for that I need quadratic forms. Now if you remember the definition of Gij mat, actually if I have I here and I here, then it's a quadratic form. So basically the diagonal entries from Gij mat give me nothing but the quadratic forms corresponding to n values. n observations. Okay, so let me call Qn as diagonal of Gij mat. Okay, and if I order them, that would give me my sample quantiles. So SQ is sort Qn. Okay, so the sorted values are nothing but sample quantiles. Now we have to worry about population quantiles. So in population quantile, we need to compute inverse CDF at 1 minus 0.5 by n, 2 minus 0.5 by n, and so on. So let me first create a sequence of 1 to n, and I need to subtract 0.5 from that. So let me do that, and I need to divide it by n. We'll confirm if it is giving correct things. So head, let me say head tail of s. Head tail gives me first few values, and I don't know, it works probably only for matrices. It should work. Okay, let's give head s. Okay, so first value will be 1 minus 0.5 divided by 50. So 0.5 by 50, 0.5 by 50 is 0.01. Okay, so it is correct. Similarly, tail of s. So last value it is taking as 0.99. It would be 50 minus 0.5 divided by 50. So 49.5 divided by 50. So it is 0.99. Okay, so this seems correct. And now I want to compute inverse chi-square PDF at these points. So those will become my population quantiles. Population quantile is Q chi SQ. Inverse CDF is nothing but quantile. So Q chi SQ at S with degrees of freedom equal to P. Okay. Q chi SQ will give me inverse CDF, and then degrees of freedom as P. And now let us plot these. So plot sample quantiles versus population quantiles. Okay, and to confirm that, see, you shouldn't trust on this as a straight line because the scales might be different sometimes. Here they are same, but sometimes they might be different. So I should always draw a straight line here. So AB line 0, 1 would give me a line with 0 intercept and slope equal to unity. Okay, so you can see that the QQ plot would say that these are probably not coming from normal distribution, because initially it seems okay, but here the distance is quite large. In fact, you would observe this in many cases, that the reason for this is the Mardias test for skewness as well as kurtosis. Both these tests are very conservative. In a sense, they generally don't reject H naught. Okay, unless it is very extremely significant, the H1 is, unless the difference is extremely significant, they generally tend not to reject H0. So many a times you might see that the QQ plot is not good, but still the tests accept the null hypothesis. Okay. So yeah, I think this is all you have to do in this practical. This matrix plot is just, just to introduce you to the command. So there is a command called pairs, which can give you scatter plot of pairs. Okay, which can give you scatter plots matrix plot. Okay, but you might have already learned this in regression, so I don't need to emphasize on that. Okay, so now you know three methods for testing multivariate normality. One is by test based on skewness, another is by test based on kurtosis, and the third one is via QQ plot. Okay.
Let me stop here. Thank you.